Today is 8:21. We are going fast. Do you see the marbles behind me? We're down to 148 to go. Ah, right. Good. Cubes. We won't actually get to the meat and potatoes part of this lesson for about the first 5 minutes. So the first 5 minutes, you might wonder, where are these cubes you mentioned? And I just decided I wanted to kind of show you the flow of how certain things happen, and then we'll transition that over into cubes. And I hope I hope this doesn't take more than 20 minutes, 15 ideally. And I hope you pick up the idea of like, this isn't just black magic, like witchcraft, like it happens for a very specific reason. So let's just real quick warm up. I put on my note card that I wanted to warm up with just a really simple, very basic, almost like pre-algebra level multiplication question. So let's just practice warm up, and let's multiply out 2x plus 5 times 3x minus 1. Thank you. So most of the time in algebra, when we multiply out a pair of binomials like this, nothing really exciting happens, right? This ought to be just complete common knowledge for you. So if I said, hey, I need you to multiply this out, you would do 4 multiplication problems, huh? So you would multiply the 2x and the 3x, and you'd get 6x squared. And then you'd multiply the 2x and the negative 1, and you'd get negative 2x. And then you'd multiply the 5 and the 3x, and you'd get plus 15x. And then you'd multiply out the 5 and the negative 1 and get negative 5. And then you'd combine the terms in the middle, and it's just business as usual. There's absolutely nothing noteworthy or remarkable about this math problem. It is just a pair of binomials multiplied together to get a quadratic trinomial. But at some point in Algebra 1, and then over the last couple of days, we rediscovered these, what we call special cases. And so if I gave you a multiplication problem that was a little bit less arbitrary, like if I put forth a little more effort in writing the problem, something unique happens. And this is what I want to tie into today, is that this is not just any old pair of binomials. You probably know from the work you've done the last couple days that something special is going to happen. Do you know already off the top of your head what it's going to be? What is it? We won't have a middle term. Thank you. So sometimes just the construction of our multipliers make things happen. If we were to multiply this out, yes, we would get 3x times 3x, which is 9x squared. But I'm gonna color code these ones just so we can identify that in the end, we really don't even need to acknowledge them. If you multiplied out this one and this one, and this one and this one, if you did those two reds, what would you get? Nothing, right? You get a negative 12x and a 12x. And again, you've been working with this concept as you factored differences of squares over the last couple of days. So not all multiplication problems are created equal. This one, if I multiplied it out, does not look like his predecessor. It looks like 9x squared minus 16. The only problems that really wind up mattering are the two white ones, because the red ones killed each other. So as we work today's lesson, I want you to think about the fact that this isn't just like a weird thing. It's not some like crazy formula. We're going to be working today with binomials and trinomials. So the multiplication problems for the first couple minutes will be longer, and the factorings when we get done will look longer. It looks really hard at first when we do cubes, bless you, and then we realize it's not bad at all. So to transition over into cubes, does that make sense so far? That not all multiplications are created equal, right? So to transition over into cubes, the first thing I wanted to do was just warm up with a problem that has absolutely no redeeming qualities. This would have been something that you did on a quiz in Algebra 1, for some of you a year ago, for some of you a couple of years ago. So what we have here is an example of a binomial being multiplied by a trinomial. And how many multiplication problems will it take for us to get going into the process? With by and by, it takes 4, right? Boom, 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 boom. How many will it take to do a by times a try? Nope, will be 6. There are 2 multipliers, each of whom multiplies by 3 things. And if 2 things do 3 jobs each, 2 times 3 is 6. So we can expect to have to do 6 different problems before we can really look at what this is. So when I multiply 2x by 5x squared, what do I get? I get 10x to the third. Remember that exponents join forces. And so if I had an x to the 1 and I multiply it by an x to the 2, I get x to the 1 plus 2, which is 3. And then I have to head over and do the second distribution. I'm staying with the 2x, like he's still like up to bat, so to speak, but he's going to go and hit the second one. And what is 2x times 7x? Nice. Right, and then we're going to head all the way across. We're still letting 2x do his thing. And what's 2x times -4? -8x. I figured, all good. Now we have to head to the second distributor, and his name is -4, or +4, excuse me. And so +4 is going to now also do triple distribution. So when 4 multiplies by 5x squared, what do we get? 20x squared? 20x squared? Because he doesn't have an x, so he doesn't get to join forces, right? Notice how I'm writing this. I showed you this in Algebra 1, but when we get longer polynomials like this, I think it's better to organize a little bit better, a little less chaos. And then I'm going to do the second red problem, which is 4 all the way across to 7x. What's that going to be? Just x. Because the 4 doesn't have an x on it, right? And then the 4 is going to multiply himself all the way across to the -4. And what are we going to get? Yeah. And now what we're going to do is we're just simply going to combine like terms. And if you don't want to write your answer like mine, that's okay. I think it helps. The like terms are nice because now they're in line with each other. So that just helps us. So when we add our x cubes together, we just, of course, get 10. And when we add our x squareds together, we get 34. When we add our x's together, we get 20 x's. Good job. And then, of course, the constant term is what it is. You'll look back at this problem, and I hope you don't view it as a waste of time. But I want to say again, there's nothing redeeming or remarkable about that, what we just did. That was just an exercise in flexing our basic skills. We multiplied a binomial times a trinomial. We got an answer, and boo, like, whoa, that was really exciting. What I want to move us into now is a problem that to you at first will look like just another one of these. But I want us, as we work towards the answer, to really take note of what the answer looks like. And this is going to kind of feel like that whole, where do difference of 2 squares come from? Okay, so this next one will not be meaningless and arbitrary, just for the record. So we're going to multiply x plus 3 by x squared minus 3x plus 9. If I put this on an Algebra 1 test, I'd probably get a lot of students who would think like, did I do something wrong? And you'll see why, because like the answer is weird. It's cool, but it's weird. Like you might think I must have messed up. Like this isn't supposed to happen. It is supposed to happen. So let's go through the 6-step process again. And I'll just kind of color code a little better this time. So what is x times x? Nice. Right, sticking with the red theme, I'll head across. And what is x times -3x? Nice. Heading all the way then across with the x, what is x times 9? Nice. Yeah. There's probably not a chance that you have any questions at this point, I'm guessing. That was just little baby multiplications. Right, I'm going to switch colors, and we're going to take now the distributor +3, and it's his turn. So when 3 multiplies by x squared, what do we get? And when 3 multiplies by -3x, what do we get? And when 3 multiplies all the way across to the 9, what do we get? And I'm guessing that you already have spotted what it is that I intended, like why I dedicated these 2 minutes to this problem was in the hopes that you'd make an identification here, that you'd look at this and say, something's about to happen. And these are the things that I think normally make newer, kind of more less confident students question themselves. What happens? A whole lot of stuff cancels out. Very good. And so really what happens is you're like, ooh, when I combine like terms, I get x to the third. Okay. But then the x squareds cancel. That's interesting. Like that's that whole sort of difference of squares thinking where those middle terms canceled out. And to make it even better, the linear terms canceled as well. And we're left simply with this. And then I think I can say now for the first time, you're seeing something, and I want you to put a name for this in your notes. This is something we're going to be working with now for a couple of days. This is called a sum of cubes. And we call it that because, well, duh, that's literally what it is. Like, what does the word sum mean? We're adding, and what are cubes? Well, cubes are things that are obtained by cubing something else. So if you think about it, like what had to be cubed to make x cubed? That's as easy as you think it is. So just x, right? And what had to be cubed to make 27? Good. So identification of that, like the fact that it looks like that is not happenstance. It didn't just happen. I did that to you on purpose. So x cubed plus 27, you'll see guys just like that for the next couple of days. That's called the sum of cubes. All right, let's do one more, and then I'm going to show you how to factor sums and differences of cubes, and we'll be off and running. So we'll do some practice. I got 4 practice factorings after this. So here is another, at first, maybe seemingly arbitrary multiplication problem. But it's not. Now that I've let the cat out of the bag, you probably know where this is headed. We're expecting a short answer here. Logically, at this point in the lesson, let's let it happen, kind of watch it happen, be a part of it happening. What is 4m times 16m squared? It is 64. How many m's will we have? Nice. All right, we're going to take 4m now all the way across to the other plus 4m, and what do we get? Plus. Yeah, we got a positive and a positive there. And then we're going to take the 4m and multiply him all the way across to the 1. And what's 4m times 1? Nice. At this point, nothing. But here it comes. Kind of watch the flow of how this happens. And again, it isn't happening just by luck. Like these were written a very certain way. I'm trying to connect so that in 3 minutes, when I show you how to factor, you can go back and look at these and see the pieces and like how they fit in. So it's actually pretty cool. All right, now we're going to take the distributor -1, and it's his job. It's his turn. What's -1 times 16m squared? Nice. And there's our first cancellation that we would have expected at this point in the lesson to see. What's -1 times 4m? Number 2, right there. And then finally, what's -1 times +1? -1. And as expected, when we combine like terms, what we see is a short answer. So when we add downwards, we wind up with 64m cubed. The m squareds cancel. Neat. The 4m's cancel. And then the -1 comes down. And then for the first time ever, you are now seeing, what do we call this guy? Yes. This is the aforementioned difference of cubes. These are what you'll be factoring. Things that look like that. That 64m cubed -1 is what you'll be factoring. And I've tried to provide you with the tools. It's not perfect, but to allow you to see why, when I show you what I'm about to show you, why it works the way it does. These answers are not just luck, like they happen for a reason. So I'm going to throw a formula at you now, actually 2 of them, and there's about a 42% chance that you're really not going to like them. So here are your formulas. Write these neatly, separate them, put a box around them, because you're going to be flipping back and referring to these for quite a while until you commit them to memory. So first we have a sum of cubes. And a sum of cubes looks like this. Don't be taken aback by A and B. A and B are just any items that are cubed. Okay? Whatever A and B are is yet to be seen. But if you get a sum of cubes, something cubed plus something else cubed, it will always factor beautifully down into what we call short set, long set. We're going to say that a lot in the next few weeks, short set, long set. So the short set consists of A plus B, and the long set will consist of A squared minus AB plus B squared. And I go, what are these A's and B's that you're talking about? Well, they're the things that had to be cubed to make the problem. There's another version of this formula, and it's very similar. I'll switch colors here. It's a difference of cubes. And instead of A cubed plus B cubed, it's A cubed minus B cubed. And it also is short set, long set. Anyone paying really close attention, looking back at the last example that we did, want to tell me, take a guess of what's going to go in the short set? Nice job, Kate. Nice job, you guys. A minus B. The A and B are still placed in the short set, just like that. The difference is that the minus goes there. Anyone want to take a shot at what long set's going to be? A squared plus AB. Geez, I must have made a lot of marks there. Plus B squared. What we come to notice, and this will be so stuck in your head by the end of today, probably already, is that each formula has one minus in it. So the thing is, it's easy to remember. I always, when I was your age, long time ago, I learned it as there's just going to be one minus. I know that, only one. And the short set mimics the original problem. So like if the original problem is a sum of cubes, short set is a sum. If the original set is a minus, a difference of cubes, then the short set is also a difference. So the minus just kind of flies to wherever he needs to go. He's like, well, if I didn't get used here, I'll fly to the middle of long set. If I did get used here, no more. I'm done. Got that? Now let's put these formulas to use, and this will be the last, I don't know, 5 minutes of the lesson. We're going to actually now put into practice the purple and red formulas, and I'm going to put up here a problem and ask you to help me factor it. So here it goes. We're adding this now to our repertoire. Like we already have difference of squares. I know if I said to Shanessa, hey, look at x squared minus 16, she'd go, oh, that's a difference of two squares, x plus 4, x minus 4. I want the cubes now to become that quick, that like quick response. So first off, is this a difference of cubes? Sometimes I have people weeks into this go, how can I tell? And I'm like, man, I suck. Make sure you know the answer to that question. Yes, it is. These are cubes. What cubed makes x cubed? X. Write that down. Writing down your A and B values will separate you from someone who doesn't. What cubed makes 8? Write that down. Now, when you look at the purple and red formulas, the A's and B's, they're all over the place, but we're simply going to replace them with the green things. So we're going to factor this down because it's a difference of cubes. We're going to factor it into a short set and a long set. Let's do this for the first time officially. What will the short set be? Say it again. Good job. A minus B. In this case, x minus 2. Well done. Now, the first thing we encounter in long set is a squared. And if A is x and B is 2, so these are A and B, by the way. I didn't say that over here because sometimes if the problem actually has A's and B's in it, this can get really confusing. But like, I hope you're seeing that this is A, right? X down there is A and 2 is our B, right? So we're just putting them in. So what's the first thing we're going to write in long set? x squared, that's a squared, plus 2x jackpot. That is how you factor a sum or a difference of cubes. You simply identify your a and b values and you plug them in. Let's go again. That's it. I mean, you got to admit that once you see it, it's like a trillion times easier than quadratics. Quadratics, I'm saying it again, they can really be a pain. All that stuff about trying like numbers that multiply to make 24, and you got to try 3 and 8 and 8 and 3. This is not about that. This is not trial and error. It's a formula. Math people really appreciate formulas because they're repetitive. Our first job is to identify, answer the question, is it a sum of cubes? Yes, and that's where that piece of paper will come in handy. Until you've learned your cubes, you might not have walked in the room today knowing that 125 is a cube, but you'll leave knowing for sure 125 is a cube. Is 27m cubed a cube? Yes, it is. So what is the cube root? In other words, what cubed would have had to make 125? Therefore, our a value is 5. What cubed, or in other words, what's the cube root of 27m cubed? 3m. Writing those down, I wish I had a more awesome color than green just to show you. Please, if you take anything away, write those down. Having them sitting in front of you will change the whole game. Because now it's a simple game. All Steve's got to do is just write his short set, long set, and plug those little suckers in. And don't switch the order because you feel like it. Some cubes will look a little more uncomfortable with the number and then the variable values. Some, as you'll see in the next example, will have 2 variable values. Just leave it as it is. Take it as it comes. All right, let's do this. Short set. Long set. Thank you for that. Yes, 5 plus 3m. Notice this time we put the plus in the first set because the problem has a plus. That means we have yet to spend our minus. What's going to go first in long set? So 25. Make sure you do the math when possible. Don't leave any math problems yet to be done. If you say 5 squared, write 25. What will go in the center? Ooh, good job. Minus the product of A and B, minus 15m. And what goes at the back? Say it again. Try it again. Try again. Thank you, Steve. Plus 9m squared. Remember, when you square something like 3m, you have to square both parts of it. You square the 3, but you square the m. Both parts get it. That is how you factor the sum of simple cubes. Next one. Ready? Is it a sum or a difference of cubes? Difference. And they are cubes, right? You can assume everything today is going to be cubes because that's what we're talking about. But like as we press forward a week and a half from today, you're going to have to not just assume, oh, it looks like it, I'm going to call it, you got to verify, vet it, make sure it's what you think it is. And yeah, these are both cubes. So what is the cube root of that? What is the cube root of that? Nice job, guys. You're doing great. Once I have those pieces, all I got to do now is construct short set, long set, piece of cake. Short set, long set. Try again. Try again. Try again. Y minus 4x. Remember that short set will always mimic the problem. That's your kind of jumping off point. Short set, mimic the problem. Okay. What goes first in long set? Very good, Hugo. What goes second? Signs are everything. Plus 4x, y. And at the tail end of long set is plus. You've already used your minus. There will never be double minuses, okay? Plus, nice. Do you feel right now, like scale of 1 to 10, like you're feeling like you're about an 8, right? This is easy. This is good. I'm going to give you one more example because I have to. And if you want another one of these, let me know and I'll conjure one up and then I'll be done and you can work however much. We don't have a lot of time, but it'll be some. Sometimes the leading coefficient is a negative and we don't want to work in such a hostile environment. So for example, this is our last example, like I said, unless you tell me you want another one, if this confuses you. As you're going to hear me say a lot in the coming weeks, we do not, mathematicians, we do not like to factor things that start with negatives. The minus in the middle, I got a tool for that. That doesn't bother me. But what I'm trying to train into you is the fact that negatives at the beginning are no bueno. Don't do it. So what we're going to do is we're going to kind of mark that with a sad face and say, you're no good. I can't have you there. So what we're going to do is we're going to pull a negative out of the whole problem before we go in. This will be a very, very common theme in the coming weeks, pulling out a negative. And we only pull a negative when the first term tells us we should. No one else will ever dictate this. There can be minuses all over the dang place, but if there's a negative in the front, no, get it out. So what we're going to do is we're going to take that negative out and we're going to rewrite the problem. What's going to go in the white parentheses is the math problem that we'll do. What's left of negative 8v cubed if we pulled out as negative? Good job. And what's left of minus 729w cubed if we pulled out his negative? He's a plus now. Pulling the negative out allows us to get always into a comfort zone. It always allows us, for the record, you might encounter a professor at a later date who tells you you don't have to do that. They're not lying to you. I'm telling you, as a matter of experience and preference, you should always yank the negative off the front end. Because if you don't, you go into your short set, long set factoring with a negative A value and a negative B value. And then as you start plugging in negative A's and B's, it's like, oh my God, it feels so. I hope you trust me. Negative in the front, get it out. Now let's factor the white thing. Forget the red negative for about the next minute. Let's do this and then we're done. So red negative will just come back on later. Forget it, put it in timeout, tell it to go take a break. What is the cube root of this? 2v. What is the cube root of this? 9w. I got my A and my B and I'm still ignoring the little red negative. Like, you just sit over there. Not worried about you right now, okay? So my answer is going to look like this. Negative, short set, long set. And don't let that negative bother you. It's going to hang around like a bad cold. Just let it sit there. What's going to go in short set? What's going to go in long set? That's not the answer I was hoping for. The rest of it. Thanks for that, helper. Do a little better. Now that's better. Good job. 4v squared. What's going to go in the center? It's not going to be a plus because guess what? We haven't used our minus yet. If you hadn't used it in the first set, it's going to go in the middle of the long set. So minus what? Yes. And I am going to alphabetize. I think B comes before W, so I'm going to call it VW, Volkswagen. Question is, do I have to? The answer is nah. It's just what you should do. What goes at the back? Plus. And that concludes the lesson. I think you are now armed and dangerous. I think at this point, for now, you can factor cubes. I'm going to pause this at least, hand out today's paper. Won't be surprised if you get almost all of it done. I mean, I was only 9 or 10 minutes, but you're gonna smoke through this, I think. So let me pause this real quick. Want some help? For problem number 4, it starts out, and like I said, I know we were far enough into the lesson that it's hard to keep listening this late, but when your problem starts with a negative, you do not want to leave it alone. What you want to do is yank the negative out as what we call a greatest common factor. So I'm going to pull the negative out front, and what's left over when I do that? 27u cubed plus, there you go. So what I'm trying to color code, what's left in white is the actual math problem we're going to factor, get the negative out of the way first. Good. Why are you doing okay?